Alright, here we go. So at the beginning of the year, if you remember, we talked about calculus was made up of 3 big topics. And so far, we've covered 2 of them. So raise your hand if you can tell me one of the 2 big topics we've covered. Ivan? Limits. Limits is 1. Second one we just finished, Ryan, is derivatives. So we're going to go to our third and final topic. Abby? Integrals, or integration. So we're looking at integration. We're going to start that today. All right. So what does this tell me we're wanting to do to f of x when I write it like this? It's wanting to take the derivative, and the derivative of f of x is f prime. Okay. And here we're wanting to take the derivative of the first derivative, which is going to give me second derivative. Okay. And this process is called what? Derivation. No. That process is called differentiation. When you're taking the derivative, that process is called differentiation. Alright. Can someone tell me how integrals and derivatives are related? Somebody besides those 2 back there.
Is this where you start with the derivative and try to turn it back?
Alright, so what's the word?
Inverse.
Kind of. I'm thinking of a different word though. Alright, what's a different word than
Indifferent.
Integrate. If you're against something,
Non-differential.
or you're the opposite of something, you are anti.
That is so.
So, anti-differentiation / integration, same thing there. So, anti-differentiation with the keyword anti tells me that I'm doing the opposite of differentiation. Make sense?
Yes.
So that's what we're getting into now. Okay. So instead of taking the derivatives of stuff over here, I could start with f prime, and we'll talk more about all this stuff right here later. So this sign right here is my integral sign, which tells me I'm wanting to take the integral of this, which means I'm wanting to do the opposite of the derivative. So if I do the opposite of the derivative to f prime, what am I going to end up with? I'm going to end up with f. And if I do the opposite of differentiation for f double prime, I'm going to end up with f prime. Okay, and we'll get more into what all this is tomorrow. Okay, but this gets us started. Questions on this so far? Alright, so there's 2 types of integrals. There's that, and there's one that looks like this. This one right here is called an indefinite. That's called an indefinite integral, and this one is called, what do you think? Definite. Okay. Why do you think one of them's called definite and one of them's called indefinite?
One has an interval and the other doesn't.
Alright, one of them has an interval and the other one doesn't. So this A and the B right here tell me the interval we're dealing with. This one does not have an A or a B, so that means there's no interval, which means it goes on forever. So definite versus indefinite. Today, we're going to be looking at the definite. And you'll have to slow me down sometimes today because, this is stuff I get excited about. That's good stuff. That's good stuff. All right. Most important takeaways from today. If we can get this erased.
You doing homework tonight, Clay?
Probably. Is Taryn in here?
No, she's not. Pretty awesome.
No, that's not what I want. I don't want the prime. Terry, can you run down the printer for me? In the main office. All right. Here's the main takeaway from today. You've got to go home with this today and remember it and remember it and remember it and remember it. Okay? As soon as you see, what is this thing called? As soon as you see a definite integral, these two things we're about to write down should pop out in your head every time. All right, I see a definite integral, that means this or this. Okay, so every time you see that. All right, so first translation of it. Okay, if I'm integrating f, where does it take me?
F prime.
No. If I integrated f prime, where did it take me? F. How is f related to f prime?
Is the anti-differentiation?
No, in levels. How is f related to f prime? F is above. Okay? So when I integrate something, it takes me to the function that is above. So it's the change in the function above across the integral. Okay, so when you see a definite integral, you need to know that represents the change in the function above across the integral. What do I mean across the integral?
In between.
Yeah, in between, from A to B. Okay, so this thing tells me the change in the function above f, from A to B. That tells me how much we're changing from A to B. Got it? Second thing is, it represents area under the curve of the function across the interval. Okay, so it represents the area under the curve of the function across the interval. Okay, and this right here is what we're dealing with today. Okay, but when you see a definite integral, I'm going to ask you what two things does a definite integral represent. You're going to tell me the change in the function above across the interval, or the area under the curve of the function across the interval. That's what I want to hear every time, and I mean, I'm going to be asking you almost daily from here till the end of the year. Okay, extremely important that we understand what this definite integral represents. Okay. Now, when we find the derivative of something, what does the derivative give me?
The change of the table.
I can get critical points from it. What else? What? I get relative extremity. What else? But what does the derivative represent?
Slope of the tangent.
What does the slope of the tangent line represent?
Range.
There we go. There's the word I'm wanting to hear. Everybody hear what Liddy said? Rate of change. Okay, so when I'm taking a derivative, I'm getting a change, but I'm getting a change in the rate. Okay, I'm getting a change in the rate. Okay, when I'm integrating, I'm still getting what? I'm still getting a change, but instead of a rate, I'm now getting it in just the functions. See the difference? So when you take the derivative, you're getting a change in the rate. When you integrate, you're getting a change in the function. Okay, a change in whatever that function is above. Got it? When you take the derivative, it's a change in the rate. Integrate, just a change in the function. That's the difference. Got it? All right. We're going to go through some examples here. You don't need to write it down. You can go back and watch the video. I just want you to pay attention.
What's Riemann's sum?
All right, it's not Riemann. It's Riemann. Okay, so Riemann sums are ways to approximate what a definite integral represents. Okay, instead of finding the exact value, we're going to use a Riemann sum to get an estimate of it. Okay, because sometimes you don't have the actual function, but you can still get an estimate. Okay, just like when we weren't able to find IROC, we estimated it with what? Error. Okay. When I can't find something, I can always estimate it. So that's what's going on with Riemann sums. Okay. So I have this table of values. Okay. It says the volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differential function r of time t, where t is measured in minutes. Okay. Between 0 and 12, the graph of r is concave down. The table above gives selected values of the rate of change r prime of the radius of the balloon over the time interval from 0 to 12. The radius of the balloon is 30 feet when t equals 5. All right. It says use a right Riemann sum with 5 subintervals indicated by the data in the table to approximate. All right. Can somebody read this for me? Have we talked about how to read it yet?
No.
Good. Here's how you read these. All right, this little symbol right here is the integral. So we're going to say it's the integral, and then you go from bottom to top. So the integral from 0 to 12, and then you say of whatever's inside. So this is the integral from 0 to 12 of r prime. Okay, that's how we read it. Okay, the integral from 0 to 12 of r prime. That's how I want it read. And we'll talk more about that tomorrow, I think. All right, now raise your hand, please, if somebody can tell me what this thing represents. What does the integral from 0 to 12 of r prime represent?
The rate for the radius is changing.
Abby?
Change in order.
Keep going.
Across the interval 0 to 12.
Very good. Everybody hear what she said?
No,
All right. She said this represents the change in r. How'd you get r? How'd you get r instead of r prime, Abby?
Because r is 1 above 1 prime.
Okay. Because we know the definite integral represents the change in the function above. So the function above r prime is r. So she said the change in the function above, which was r, from 0 to 12. Perfect. Okay. All right, then use correct meaning. So we're going to take what she said, and then we're going to be a little bit more specific with it. All right. So first thing I want to do is I want to plot these. I want to plot this information here. Okay. All right. So we have 0 and 5.7. Where do we go? We go to 5.7 and then 0.5. So 1, 2, 3, 4, 5, 6. So 0, 5.7 is somewhere in there. 2 and 4 is there. 5, 3, 4, 5 and 2. Pretty close to there. 7 and 1.2. 6, 7 and 1.2. 11, 8, 9, 10, 11 and 0.6. So somewhere in there. And then 12 and 0.5. So somewhere in there. So there are all my data points. Okay, so if I were to connect these, I don't really know what it looks like, but if I were to connect these, something like that. Okay. Now, Abby gave me one meaning of this. Somebody raise your hand and tell me what the other meaning of this is. Somebody besides Abby and those two in the back. Ethan?
The area under the curve of the function across the interval.
All right, so the area under the curve. So I'm now going to use my graph and approximate the area under the curve. And we're going to approximate it with a bunch of rectangles. Okay? And we're going to use the values they gave me. So they said 2, 5, 7, 11, and 12. Okay? So I'm going to use those windows and I'm going to make rectangles. Okay? So I'm going to come up and I'm going to draw a rectangle. Now there's two types of rectangles we're going to start with. Okay, and if you notice, this one says right. Okay, right tells you which side to go up on and make the top of your rectangle. Okay, so right means in my first window right here, I'm going to go up. And am I going to stop at the left or am I going to stop at the right? I'm going to stop at the right. That tells me which one to stop on. So if I go up and I go over, there's my first rectangle.
So what if it is? What will there be a chance where it's like just use the Riemann sum without telling you if it's right or left?
No. It's going to have to tell you right, left, midpoint, trapezoid. I think that's all of them.
So So if it said left, we'd go all the way.
So if it said left, I'd have gone all the way up to the top, and I'd have had a taller rectangle. Understand the difference between a left and a right?
That wouldn't be under the curve.
It doesn't matter. It's an approximation. You can have an over approximation, you can have an under approximation. Okay, so now I go up here and I go over, I go up and I go over, I go up and over, and then there's not much going on there. Okay, so there are all my rectangles. So Carter said, well, if I go to the left, I'm going to have an over. My rectangles are going to be over. Okay, here all of my rectangles are where? They're under. So if my rectangles are under, what type of approximation am I going to have? Under. If they're on top, they're going to have over. Over. All right. All right, so I need, now what do I want to do with each one of these rectangles? I want to find the area. Okay, so on this one, I know it's too wide. How tall is it? It is 4 tall, so that means my area of that one's going to be 8. Okay, this one is 3, and how tall? 2, so 3 and 2 gives me 6. The next one is 2, and how tall? 1.2, so 2 and 1.2, 2.4. And then the next one, 1, 2, 3, 4, and how tall? 0.6, so that's going to be 2.4. And the last one is 1 and 0.5, so this one's going to be 0.5. So I found the area of all of my rectangles. Now what do you think I want to do with it? I want to add them up. All right, so 2.4, 2.4, that's 4.8. This is 14, so that's 18.8. So that makes it 19.3. Okay. So my approximation of this right here is 19.3, and what should my units be? And then tell me why, because this is something we haven't talked about yet. Ethan?
Is it feet?
Feet. Okay, Ethan, how'd you get feet?
Because when we're taking derivative, it would be feet per minute per minute. So if we go the opposite direction, we just take per minute out.
Very good. Everybody hear what Ethan said? He nailed it. Okay, usually when I take the derivative, if I did r double prime, it would give me feet per minute squared. So, I mean, logically, if I'm going the other direction, what's going to happen? I'm going to lose a unit from the bottom. Okay, so if I'm feet per minute squared on r double prime, and then feet per minute, and then that means the next one is just feet. So I end up with just feet. Now, there's another way to do it. Usually, when you have an x and y axis, they will give you the units for your y axis. So in this case, what would the units of my y axis be? What? Nope. This would be feet per minute. Okay, and then my x axis would be minutes. Okay, so feet per minute gives me that. Minutes gives me the other one. Now, what did we do in here? We multiplied, right? So we multiplied this by that, right? Which means I do feet per minute times minutes. What happens? The minutes cancel and I get feet. Okay, so again, it goes back to what I tell you all the time. What is it? Units are your best friends. Okay? This tells you, when you look at your units, it tells you that you did it right. Make sense? Okay? So you can think of it both ways. I'm going up, so I need to drop a time limit, or I multiplied, so that means my minutes cancel. Got it? All right, good stuff. Now, I want to be able to do this without drawing. So I want to be able to do that same thing without drawing it. So can somebody talk to me about what we need to do to be able to do all that without drawing? Ryan?
Since you have an x and a y, you can plot those, or you can use them as points to find distance between points, and then you can use that to approximate your rectangles.
You're making it way complicated. It's super easy. Abby?
Oh, no, you go. Okay, I mean, like, you could just, since you, like you said, you have your points, so you could just count, like, you know how far away each of them is going to be, so you can count your sides, and then since it says right, you know that your curve is going to look like that, like, go that direction, so you know it's going to be at the points that it
You're saying it, but you're not nailing it. You're hitting a ground ball instead of a line drive. What do you got?
But like how is like so the minutes, so there's 2 points in between 0 and 2, and then like since it says right, use the numbers on the right.
There you go. That's what I'm looking for. Okay. I need to know how far is it from here to there, and then since it said right, I'm going to use that value. Okay. So how far is it? 2. And what's my right value? 4. Okay. And then I go plus. How far is it? 3. What's my right value? 2. Because you need a visual. You got to have a visual first. Because if I just started this, you wouldn't have any clue what it is I'm actually doing. You need to see the rectangles. Okay, but you don't have to go back. You don't have to go back and draw it now. You just now you understand what's going on. So now we don't have to draw it. Okay, but I needed to draw it to give you the visual, to give you the units, all that type of stuff. All right, how far? 2. 1.2. How far? 4. Right? 0.6. How far? 1.5. I get the same answer. Got it? All right. And we ended up with what? All right, 19.3 feet. All right, so let's take what Abby said. Abby did a pretty good job of explaining what this is. Now we want to be a little bit more specific and apply it to this problem, okay? Because it says, explain the meaning of this in terms of the radius of the balloon. So can somebody tell me what this 19.3 represents? Raise your hand, please. Alidi?
Okay. The change of R from the interval 0 to 12 is approximately 19.3 feet.
Good. I want you got it, but I want to be more specific.
Okay.
What type of change? What type of change was it?
Positive?
Did it go up? Did it go down? Did it increase? Decrease? It increased. How do I know it increased? Because this is positive. Okay, so what increased? What was it that increased? Anybody? Radius. So it's the increase of the radius in feet from 0 to 12 seconds. So let's reword that. So what does this tell me happened? My radius increased. So the radius increased 19.3 feet from 0 to 12 seconds. Or minutes. Very good. Okay? But we usually need to start with what Abby and what Alidi were saying. Start out with something general and then make it apply to this problem. Okay? You need to understand what it is you're talking about. Okay? This problem was talking about a radius. Okay? So my radius increased this much from 0 to 12 minutes. Okay? Make it specific to the problem. Okay? Get a general idea and then translate that to something specific. Yes?
The fact that the balloon is 30 feet, or the radius is 30 feet, that's e equals 5, does that mean anything to us?
Not on this part of the problem. Another part of the problem, yes.
Okay.
Okay.
So you know how you said there's 2 ways to say it? Like, could you do the same thing like with the area? So like you said, like the area of under the interval would be 19.
Right. Okay. Now that's a great question. Whenever you're going to explain what it means, you're always going to use the top one. Okay. You're not going to use the area one. The area one is what you use to help you find it. The top one is what you help use to explain it. Make sense?
No.
Good question. What do you mean? Remember those 2 explanations I put over here?
Okay.
Okay. The top one is what you use to explain what you found. The bottom is what you use to find it.
Okay. I was looking at the top and bottom.
No, I'm talking about what I wrote on the board a while ago.
So why didn't you say radius increased approximately 19.3?
Well, I could if I wanted to, but in this case, when they're wanting the explanation, they're just wanting you to use the value they found. Okay, if you said that, you'd be fine. All right, next one. bring that down a little bit. All right. Rocket A has positive velocity v after being launched upward from an initial height of 0 feet at time t equals 0 seconds. The velocity of the rocket is recorded for selected values of t over the interval from 0 to 80 seconds, as shown in the table above. All right. So using correct units, explain the meaning of this. Use the midpoint sum. So I want to do this first and then go back and explain it. Is what I want to do. Okay. Now this time we've got a different word here. We've got midpoint.
So that means you cut it in half. 22
0
points.
to 10, 0 to
All right.
5.
That's a good thought. We're going to make it easier than that.
Since 3 intervals, you would take 10 to 7 split into 3 intervals and use the middle number in between.
All right. Here's the trick. Now notice where does this one want me to start? 10. So don't make the mistake of starting at 0. Okay, so I need to start at 10. Okay, and I need to stop at 70. Okay, and then as Ryan said, it said 3 subintervals, but I'm going to make it easier on you than that. Okay, whenever you have to use a midpoint, you always want to skip one. Instead of going from 10 to 20 like we did last time, we want to go 10 to 30. So I'm going to go 10 to 30, I'm going to go 30 to 50, and then I'm going to go 50 to 70. Now, why do I want to skip one?
Because midpoint.
It's the midpoint. What do I want? I need something in the middle. Okay, so whenever you're doing midpoint, you're always going to skip one and leave you something in the middle. Okay? So, now we're ready to approximate it. All right, how far? 20. And what do I want to multiply by?
30. I thought it was all right.
22. Because what am I doing? Midpoint. I need the one in the middle. Okay. How far on the next one? 20. What's the one in the middle? 35. How far? 20. The one in the middle? 44. Somebody with the calculator, knock that out for me real quick. So we could just do 22 plus 35 plus 44 and then take that times 20. Since you can factor the 20 out. 2020?
Yeah.
So 2020, all right, raise your hand if you can tell me what the units need to be. Carter?
Is it feet?
Feet. How'd you get feet?
Seconds cancel out.
Say it again.
Seconds cancel out.
All right, so you can think of it two ways. I integrated velocity, which means I need to go up, and I need to lose time, which gives me feet. Or I can look at my units right here and multiply. So I have seconds times feet per second. The seconds are going to cancel. So either way, we end up with feet. Zach.
So basically, if whatever you say, we have inches or whatever. Basically, if you're looking for your original function, not the derivative, you're not going to have feet per second or feet per second squared.
Well, I mean, if I started with feet per second squared and I integrated feet per second squared, what am I going to get?
Feet per second.
Feet per second.
But you can have a derivative, first derivative that's feet per second squared.
No, I'm saying
Yeah. So if you start at the second derivative.
if I start at the second derivative, I'm going to get the units of the first
Yeah.
derivative.
So whatever you're finding is it's kind of easy. So like feet, it goes feet per second, then feet per second squared. So that's easy.
And then it goes the opposite the other way. All right, now somebody that hasn't talked yet, explain the meaning of what we found right here. Okay, you can give me something general and then go back and modify it if you want, whatever you want to do, but I want somebody to step up and tell me what that thing represents. Somebody new. But thank you.
I don't know. I'll give it a shot. I could probably be wrong.
There's nothing wrong with being wrong,
Is it the
as long as you learn from it.
average acceleration between 10 to 70?
Hold on, where are you getting average acceleration from?
Part. Never mind.
Quit looking at part B. All we're looking at is
Oh.
this. All we're looking at is this right here. Natalie, what you got?
I didn't.
You're close. A little bit off. What do you got, Manny?
Height increase 20 feet from 10 to 70 seconds.
Okay, I like what she said. I would just put one more thing because she said height, but I don't know what height she's talking about. Height of what? The rocket. So I would say the height of the rocket approximately increased 2,020 feet between 10 and 70 seconds. That's what that represents. Got it? Everybody good with that? All right, now let's get into part B. Part B, we're going to have to dig.
Oh, I thought I was part B.
We're going to have to dig into some of our prior knowledge on part B. Okay? So find the average acceleration of rocket A over the time interval from 0 to 80 seconds. Indicate units of measure. All right, let me see if somebody else can get it, and then we'll come to you, Brian.
Is the same as in the previous chapter?
We got it.
Well, acceleration is the second derivative, correct?
Acceleration is the second derivative, yeah.
Okay, so hold on, I just wanted to clarify that so I now have to think about how to get that. Well, we know it's going to be feet per second cubed, but then I don't know how we can go from V of t down to.
All right, Hunter, what do you got?
V of 80 minus V of 0 over 80 minus 0.
V of 80 minus V of 0 over 80 minus 0. Explain, Hunter.
Well, okay, actually, so it'd be units is your best friend.
Units is your best friend.
You'd have feet per second over seconds, which would mean that it would be it would end up being acceleration because it'd be feet per second.
You're making me proud.
And I think I was wrong because of AROC, but then I think that isn't that kind of the same.
All right, so you're doing two things here. All right, this right here. What is that right there? What should that mean to me?
A-rock.
That means AROC. Okay, and what do we know AROC equals?
Average rate of change.
Average rate of change. Okay, which also equals an IROC. Okay, it equals an IROC. Okay, so if I wanted the instantaneous acceleration, I'm going to plug in a time value into. Nope. If I want instantaneous velocity, where am I going to plug into? Velocity. If I want instantaneous acceleration, what am I going to plug into? Acceleration. Okay? So this right here is instantaneous. I'm plugging into whatever it is I want. Okay? But if I'm doing average, what do I have to deal with? I have to deal with the one above for what Hunter said. So Hunter already knows that the units have to be feet per second squared. Okay, so that means I've got to produce something with an average that gives me feet per second squared. So we go with feet per second over seconds, which gives me feet per second squared. I get what I want. Okay, again, units are your best friend. So what is V of 80? 49. And V of 0? 5. Over 80, so we're looking at 44 over 80, and my units are feet per second squared. There it is.
It's the same thing from last time.
It's the same thing. It's all connected. You're just coming about it from a different way. Okay? Because here's the deal. What happens if I don't have velocity and I have acceleration and I want to find average acceleration?
Use the integral to get to
I use the integral to get where?
the position.
To get to, no, not position. To get to velocity.
Yeah.
Okay, so if I have acceleration and I want velocity, then I just got to integrate to get there. Okay? All right, one more example. This one has another average problem in it if you're feeling iffy on that.
So integral is to find, like, you pretty much skip this step. In the interval, so like if you had acceleration, you had time, but you didn't have velocity, then that's how you can find velocity.
Say it again.
It's like with integrals, you could, like how you find velocity, like if you were missing velocity, you could use acceleration to find velocity.
Yes. Yes, if you don't have velocity, you can use position to find it, or you can use acceleration to find it. You got two approaches to get there. Okay? If I have position, then I got to take the derivative to get to it. If I got acceleration, then I got to integrate to get to it. Make sense? All right. a metal wire length of 8 centimeters is heated at one end. So I've got a wire, it's heated at one end, and it's going to gradually heat up the rest of the wire. Make sense? So that's what's going on here. Okay? So this is one end. The further I get away to the other end, notice what happens to my temperature. It decreases because it's further away from the source of the heat. Make sense? All right. The function t is decreasing and twice differentiable. All right. Write an integral expression in terms of t of x for the average temperature of the wire. Estimate the average temperature of the wire using a trapezoidal sum with 4 subintervals indicated by the data in the table. Now, we may not get to this today, but we can definitely set it up. All right. Anybody know what we need to do to set it up to get average temperature? Somebody new. Somebody new. All right, Abby, what do you got?
Are you doing like t of 8 minus t of 0 over 55? Like, are you doing that?
All right, so what's something you could ask yourself to see if that's right?
The units.
All right, so if I did t of 8 minus t of 0, what would my units be? I'm talking to Abby. If I did t of 8 minus t of 0, I'm only using t, what would my units be if I'm just using t? What?
Centimeters?
No. Here's t. What's the units of t?
Celsius.
Degrees Celsius. Okay? And then you said it was over.
Over centimeters.
Okay? Does that give me an average temperature? What should the units of average temperature be? Just degrees Celsius. So does this give me what I want? No. Good thinking. So, what can I do to get what I want? All right, Maddie.
You just add all the temperatures together and divide them.
All right, now. Thank you for saying that. But a lot of us, when you get to calculus, you think about average and you go back to the average you've known back in your old school days, where you add it up and then you divide by how many things you got. That no longer exists in calculus. Okay? So that does not exist. Okay? So, what's something else I can do? All right, Ryan.
You can integrate temperature.
I can integrate temperature. Okay, and I'm going to integrate from where to where?
From 0.
It's from 0 to 8.
And then you do A-rock with
A-rock with the result of this?
Yes.
All right. So we'll just say that's the top. So what is the bottom? What's the bottom half of A-rock?
Oh,
8 minus 0. So we end up with 8 minus 0. And that gives me what I
Why
want.
is that on top?
Why did we put an integral on top?
Say it again.
Why did we put an interval?
Because to get average, I need the change in what's above. So to get average, I need to get above temperature. So in order to get above temperature, I have to integrate. Okay? Go back to the definitions. Go back to the definitions of a definite integral. What was the first definition of a definite integral I gave you today? Change in the function above. Okay? So this gives me the change in the function above temperature. And then when I put that on top of this, that's going to make it an average.
Roll it across so above the interval means it's that thing above 8 minus 0, right?
Say it again.
This is above the interval. It says change the function above.
Above that.
Well, so what's above it?
Yeah, that's a good question. This is one of those things where I don't have a unit for you. This one's jacked up. But you can still get to the answer. Yes.
So that's the answer because like even though 8 minus 0 is still centimeters, it's because you're crossing out. So like
Mhm.
it goes away.
You're still crossing it out.
We're finding in between centimeters and degrees Celsius. Is that what you're saying?
Say it again.
No, you said there's no definite unit, so we're finding between centimeters and on the table up there.
Yeah, so I don't know. See, that's what so we want to end up with degrees Celsius. So that means we've got to have, the top would have to be degrees Celsius times centimeters. Because, again, we go back to, what do we do with these two things? To get our units, what do we do with these two things? Since we're finding what? We're finding area, so what do we do with these two units? We multiply. So when I do degrees Celsius times centimeters, I get degrees Celsius times centimeters. I'm putting it on top of centimeters, so centimeters cancel. Gives me the degrees Celsius I'm looking for. Okay? So anytime you integrate, if you're integrating and they give you a table, just multiply those two together. That gives you the units of what's up there. Okay? Can you buy that? What's
Well, you lost me an area.
I get that.
I'm still unclear.
Remember back when we were drawing the triangles or drawing the rectangles? Okay? We were drawing the rectangles. How did I get my units for those rectangles?
You added the.
I had a unit for the vertical piece. I had a unit for the horizontal piece, and then what did we do? We found area. So what had to happen to these two? You had to multiply them, right? So you're multiplying the units. Well, what are my units? Degrees Celsius and centimeters. So that means when I integrate this thing, I've got to multiply my units. There they are. Okay? You just got to remember, when I'm integrating, what do you do with your units? Multiply.
So why are you multiplying degrees Celsius and centimeters? I get that.
Because I'm finding area.
Where's the area on there?
Remember, if I plot all this out and I draw my rectangles, okay, I got my vertical unit, I got my horizontal unit. To find the area of a rectangle, I've got to multiply these two pieces.
I follow that. So what about this equation?
Well, this right here is degrees Celsius. This right here is centimeters. So when I multiply those two together, I'm going to get this.
How do you know that's how
Because
that
that's what the
goes?
definite integral is the area, it represents the area that you're finding.
But how do you know degrees Celsius is there and centimeters is there?
Because it's what I said.
Because this is always your vertical, this is always your horizontal.
And because it says average, you put it over.
So yeah, okay, I'm getting it slowly but
For your
surely.
interval.
So then, how does the T of X? T of X is the degrees Celsius, right? Right on the S over whatever T of X. Yes, that's your degrees Celsius.
That's my degrees Celsius.
So then, what brings in the centimeter for me to multiply the other?
Here?
Yes.
Because when I integrate, that takes me up and it causes me to multiply. Because what are the, remember, that goes back to those two things I told you you've got to remember. One of the two things is indefinite interval represent.
Change the function above.
Change in the function above, okay? So I'm looking for the change in the function above this.
Okay. So that's the.
And when I integrate, that gives me the change in the function above.
Okay.
And to get the change in the function above, that goes to the second piece, which means the definite interval represents the
area under the curve.
area under the curve. That's where the multiplication comes in to give me my units.
Okay.
Okay, and I have that over the centimeters I got from the bottom. It cancels, gives me the units I was looking for to find an average temperature. Some great stuff. And I know some of you are just pumped. You got it, and some of you are struggling. Don't worry if you're struggling, we'll get over it. But if you're getting it, that's good stuff.
Say that.
All right. We don't have time. So, I'm going to pass out, and don't go anywhere, please. The bell's about to ring. Don't go anywhere. Okay, I'm going to pass out some work. If it says a trapezoid sum, skip over it. We'll get to that later. Okay? So if it says trapezoid, ignore it, move on. If you've got some setup you can do some setup. Okay? Now, I'm going to give you this assignment, but I'm going to be gone. Dr. Cobb has me gone tomorrow and Thursday. Tomorrow, definitely bring some headphones. I'm going to set you up with the notebooks or with the Chromebooks. And when you guys go and the bell rings, I'm going to record the video for tomorrow. And so you'll have a video to watch tomorrow and you'll have an assignment to watch tomorrow. Okay? Thursday I haven't decided, so bring your headphones Thursday as well. Got it? So this assignment, we won't go over